All right, here we go with 3.1. Just a single day for it. Kind of the overview of the chapter is polynomials. You'll start to notice some different stuff in 3.2, okay? You can see 3.1 should just be a review, right? The natural place for us to start with polynomials is with quadratics, which again, we've seen those time and time again. We'll take about 5 slides here today and brush up on them a little bit more, okay? Because they are the one polynomial. Well, there's technically 2, but we don't always think of lines as polynomials, but they are. Quadratics tend to kind of exhibit more of the behaviors that we expect out of polynomials. But we know, like you can see in this example, what characterizes it as a quadratic is that leading term and the fact that x is raised to the second power, okay? That's what makes a quadratic a quadratic. Basically, where we're going in this chapter is, what if that leading term, instead of to the second power, it was to the third? Or what if it was to the fourth? Or what if it was to the fifth, okay? What if that power goes up beyond 2? Okay, those types of functions, that's basically the focus of chapter 3. That's what we're going to look at, and that's where we're going. Okay, hopefully today feels like a lot of review. All right, I'm going to do a little sketch. I've got a quadratic here in standard form. Okay, so let me get all the stuff I need to graph it. Starting with the axis of symmetry. And the more I'm thinking about that, I could probably just abbreviate that and just say axis. I think you would know what I mean, right? Let's go with that. Remember, it's negative b over 2a. And just by the way, for this quadratic, a is 2, b is 8, c is 7. So I got negative 8 over 2 times 2, which will be negative 2, okay? Not a ton left. If I want to get the vertex, that's a point that's going to be the maximum or the minimum. From looking at the equation, I see that a is 2. So it's looking like this quadratic is going to open up, and it would be a minimum. The axis of symmetry always goes right through the vertex, so I already have that. I just need to get the y-coordinate, which I would get from plug in negative 2 back in. So there is our vertex. In standard form, the y-intercept is always a breeze. It's the y value you would get if you plug in 0, but it's also always c. I'm going to do one more thing when I graph this. I want to reflect a point across, but we'll do that here in a minute. In the meantime, let's zoom in here and see what we have. All right, the axis of symmetry was over here at negative 2, so I'm going to put that in. Negative 2, negative 1, that's your vertex. Then I found that the y-intercept is up here at 0. Whoops. That all sounds good and well, except I believe I put the axis at -3, which is no good. All right, there it is at -2. -2, -1, 0, 7. And I'll reflect this other point right here, which I should label what that is. I'll just put right here. From reflecting it, I got 4, -7, but that will do the trick, because once I have those 3 points, good to go. Gets a little bit skinnier quadratic, because that leading coefficient's 2. Right, that's a vertical stretch, so it's a little skinnier. It's got that vertex at -2, -1, opens up, and there you go. There's a graph in standard form. So you can probably recall from quadratics, we love to graph them. We love finding their zeros, right? Which has some applications to graphing if the equation you got was in factored form, okay? Otherwise, we wouldn't bother to find them. But remember that anytime we're working backwards to solve with a quadratic, it has to be set equal to 0 for the algebra to work out. So we find zeros, right? It's a really important thing to be able to do with quadratics. You'd be pretty limited in what you could do with them if you couldn't do that. All right, first thing I'm going to do here is I got a negative sign. Then I'm going to factor out. This one is factorable. Won't be a big surprise. The next one we look at won't be. So I need 2 factors of 8 that would add up to -6. I'm leaving this negative sign out front, but it really doesn't affect anything. Those two are pretty easy to solve, so I kind of skipped over the steps to do it, but you'd have x minus 2 equals 0, x minus 4 equals 0, right? You set each factor to 0, set it equal to 0 individually, and then go ahead and solve them, okay? Oh, just a little proof on this one in terms of it not being factorable. The only options you have to stick in there are 1 and 7. You could play around with them, but you're going to find pretty quick that it's not going to work. There's no way you could move +1 and +7 to get a middle term of 8. I mean, with the way it's set up, I'll get a leading term of 2x squared. I'll get a value of c of 7, right? I'll do that. But you can't get the middle term to be 8. Now, one thing, I'm going to back up here a little bit. This is the quadratic I graphed before, right? So just from looking at that graph, it's always worth kind of noting that, even though a lot of times we find the zeros because we're looking for a piece of information about the quadratic, it doesn't have to be the x-intercept. But for these two problems, they are, right? The zeros are the x-intercept. So looking up at this graph, I can see, I'm going to have to go to the quadratic formula because factoring didn't work, but I can see they both look to be negative. They're both pretty close together, like between -1 and -3. This is kind of a little expectation for what I'm going to get for my answers, which is always good to have. All right, there's the opposite of b, plus or minus the square root of b squared minus 4ac, all of that over 2a. Always good to pause for a second at this point, just double check and make sure, is everything where it belongs, right? In terms of finding these zeros, I'm doomed if even just one number isn't substituted correctly. I'm not going to get them. Everything simplifies pretty quick, right? We do get a positive number underneath the square root, which can be simplified. Looking right here with 8. That radical can be reduced down to 2 square root 2. And that looks great too, except, wait a minute. They all have a factor of 2, so that could become a 1. That could become a 2. That could become a negative 4. And there you go, negative 4 plus or minus square root 2 over 2. Okay, if you plug those into a calculator, you would see that the decimals, they match the graph. They're both pretty close together. They're both negative, okay? We end up getting what we're looking for. All right, one more to graph here, except this is the better form. Standard form is always kind of a lot of work. Not a ton, but more than here. This is vertex form, which is always a great form to graph because, most of the work when it was in standard form was to figure out where the vertex is. Here, that's not too much of a concern. Vertex form basically shows you right where it is. And the axis, of course, just goes right along with it. It's at negative 1, okay? I do need the y-intercept here. I have to be a little bit more careful that it's not, again, it's tempting to say that plus 2 at the end is c. It's not, right? It typically is never the number that we're looking for. That constant at the end is the y-intercept if the quadratic is in standard form, not in vertex. But that's fine. Just plug in 0. That's always the way to go. Just be negative 2 times 1 plus 2. So we know it goes through the point 0, 0. Okay? I do need to get another point to reflect, but I like to wait till I'm on the graph to figure out what that point is, okay? So we'll zoom in again. Axis of symmetry, which will go right down the middle of the quadratic, is at x equals negative 1. Vertex is at negative 1, 2, so that'll be right here. And our y-intercept is 0. It looks like just from putting that point on there, this quadratic is going to open down, which if you go back and look at the equation, you can see a out front is negative 2, so that makes sense. Right? This quadratic should be opening down. I'm going to put this point right over here. Again, I should just make note of what that point is. Negative 2, 0, which I just got from reflecting the y-intercept. Again, that's enough to see it. Got the vertex, y-intercept opens down. right? Based on all the same stuff, right? The big difference on this one, if you're feeling like, well, hey, that one was a little easier than the standard form, you'd be right. But it was really up here. And again, this form is really easy to get this stuff. And if you're graphing a quadratic, the axis of symmetry and the vertex are really important to get. And here it was easy. And again, with the standard form, it's not like it was horribly difficult. It just there was more to it than here. All right, we'll wrap it up today with a couple of word problems. If we're looking for a minimum or a maximum value, it's a common thing that we could find ourselves looking for. Okay, one thing to look at the equation, you'll find that these things always go together. If A is positive, you're going to be talking about a quadratic that has a minimum because that quadratic is going to open up. So it'll have its vertex would be a minimum. Likewise, if you have A less than 0, or, spoiler alert, this one, you're going to be talking about a maximum because you have a quadratic that opens down. Okay? I think this might be a useful little thing to do on these kinds of problems. Okay? Sketch a little, a very, very basic sketch about what's going on. Okay? It says that the x value is distance and the y value is height. And here I'm not going for any accuracy at all. But what's going on is the ball is hit and it comes back to the ground. A is negative, so I knew it opens down. And right about there, this quadratic is going to have a maximum, and that's what this problem is about, is finding where that is. Okay? Even says so right here. Where's the maximum height of the baseball? Okay. Well, as soon as I realize it's a problem about a max, I go negative b over 2a. I get 156.25, right? The coefficients obviously have some little decimals in there, which is fine, okay? Doesn't change how the formula works, even if the numbers aren't real nice, okay? Now, one thing I got to check for here, this is a big thing with a problem finding a maximum, okay, or that point that we would call a vertex, the same would apply to a minimum. Is this the number we're looking for? Maybe, okay? If I just do the negative b over 2a, this is the x value, which we had identified on our graph, that this is distance, right? When that ball is at its maximum point, it's going to be 156.25 feet away from where it was hit, okay? If I go back to the problem and double check, that's actually not what it was asking for, okay? It's very relevant because I need that number. I'm just not done yet. It wants the height, which is the y value. Now this'll look worse than it is. The concept is simple. I just have to plug the number back into the quadratic. But for this particular problem, the numbers aren't super nice, so it doesn't look all that pretty. There it is. That's just 156.25 getting plugged back in. And we get 81.25, okay? Anytime you do a word problem where you're finding a maximum, pay close attention to that, right? Do I want the x value or do I want the y value? Okay, it just either means you could stop right after negative b over 2a, or do you have to plug it back in? All right, so soft drink manufacturer wants to minimize cost based on the number of units produced, right? Comes up a lot in business problems as to where they, what amount of production would maximize revenue, minimize cost, right? There's kind of this point where the business is working at its peak efficiency, okay? This is a cost, right? So again, I'm going to make a basic little sketch here. What the problem is describing is the x value would be like the units. The y value would be like the cost. So this graph is doing something like this. And we are after the point right down there. Okay? I think it's just a nice little thing to have on these problems. A basic little sketch that's like, okay, this is what's going on. Okay? How many units a day should be produced to find a minimum cost? Well, no surprise that it's a minimum. Because again, you look over here, A is positive, so we have a quadratic that opens up and has a minimum. Okay. Our go-to pretty much every time. Negative b over 2a. In this case, that would be 10. Which I get 66.67 units per day. Which leads us back to the same point as the last one, where I look back at the problem and the little sketch I made, and I basically just ask myself, am I done? Right? Or do I have to go back and plug this number in? Okay? I said, how many units a day should be produced? The x value is units, and when I did negative b over 2a, I have an x value, which is in units per day. So unlike the other one, we're done. Okay, if I were to plug that back into our quadratic, it would give me that minimum daily cost that they would get at that level of production, which we could do, right? That would, there'd be nothing to it. We did it in the last problem. Go back to here, right? And plug in 66.67. We're not going to do it because this problem didn't ask us to, okay? Hopefully, that felt like a lot of review, right? We really have focused on quadratics. This is kind of, honestly speaking, we could have brushed over them here to get into polynomials. I think they're important enough that they're always worth a little bit of review. Plus, they kind of get us back into the polynomial mindset, okay? Because again, a quadratic is a polynomial. It shows all the characteristics that we're looking for. Okay, so really in not day 2, but in 3.2 tomorrow, we'll dive into that, right? What happens when that power goes above 2?